All right, so using the division algorithm, we're going to solve these next two problems here. So for exercise 1, we want to find the quotient q and the remainder r when a is divided by b for the following. So notice here that both b's are positive, perfect, because they have to be by the division algorithm. They have to be greater than 0, integers they are, but there is no condition on a. So I have an example here when a is positive and when a is negative, and how we treat these is going to be slightly different. All right, so let's jump into solving these. So exercise 1. So the first exercise, our A is equal to 4,327 and B is 281. So we have two ways of being able to do this. We know from the original example we can do this using long division. Long division gives us our division algorithm in the end. So let's start off with that. So I want to take 281 and I want to put this into 4,327. All right, so I take the 281 and I ask, well, how many times does that go into 432? Well, that goes once. So 281. I do my subtraction here. And what do I get? I end up with 1,000. 151. Now I'm going to bring down the 7, and that's going to make it 1,517. So I ask the question, am I at my stop condition? So my stop condition is based upon comparing the remainder, so that's my 1,571 with my divisor, which is 281. Now 281 is much smaller than what my remainder is, so I repeat the process again. So now I ask, well, how many times does 281 go into this 1,517? Well, it goes a total of 5 times. So 5 times 281 is going to get me 1,405. And I do the subtraction here, and I'm left with 112. Now again, I asked the question, am I at the stop condition? Well, since 112 is strictly less than 281, we stop. So this tells us that this 4,327 can be decomposed as the product of 15 times 281 plus the remainder of 112. Okay, but what happens if we don't want to use long division? So I said there's two ways of being able to do this, probably more than two ways, but two ways that I'm going to cover here. So the next way is if we have a calculator, let's just do the division. So if I take 4,327 divided by 281 and I put this into my calculator, I end up with 15.396. Rounded to 3 decimal places. Now this 396, that's problematic because that's not really a remainder, that's a decimal for us. So something's wrong here. So what we need to do is we just need to focus on, well, what's the whole number part of this? That whole number part is 15. So what we're going to do is we're going to round down to 15. And then we're going to use this a minus bq is equal to r. So we can find out what the remainder is by taking this 15, because 15 is in fact for us the it's the quotient. There we go. I wanted to say it's the divisor. It's not the divisor. It's the quotient. So I found out what the quotient is. I know what the divisor is. That's 281. So I know my b, I know my q, I know my a. I can figure out what r is. So this tells me that 4,327 minus b, which is 15, times q, there we go, times b, which is the 281, there we go, times q, which is our quotient, which is 15. This gets us 4,327 minus 4,215, which is 112. So there we go. We end up with exactly the same thing. So we don't really care about the decimal part of this. We just care about the whole number part of this. All right, so let's flip this example here. Let's go to the second one. So a different a, a different b. So a this time is negative 7,432. There we go. And the b, 453. Now we're not going to do the long division way. Let's just do this with the calculator. So if I put in my calculator negative 7,432 divided by 453, this is going to be equal to negative 16.406. Okay, so what did we do last time? Last time we only cared about this whole part. Are we going to do the same thing now? Well, let's say yes. Let's say we did just care about that 16. Well, what would happen? So just kind of as a note, well, what would happen is, again, we have this negative 7,432 minus a minus 16 times 453. So that's going to give us negative 7,432 plus 7,248. Now notice that the first term is bigger negatively than the second term. So the problem with this is now I'm going to end up with a negative 184. And sad face. Because if this is supposed to be my remainder, remember the whole idea of this is my remainder has to be greater than or equal to 0, but strictly less than b. So this number is negative. This doesn't work out. So I can't just leave it as 16. So what do I need to do? I need to go to negative 17. I need to make my second term in this more negative than my first term. So I want this to be more negative than this one. All right, so let's move my screen up here a bit. So again, just a note, if a is less than 0, then go one down. So instead of negative 16, this time we're going to be doing, oh, sorry, negative 16 there. We're going to go negative 17. So if I have my negative 7,432 minus 17 times 453, what we end up with is negative 7,432 plus 7,701. And this leaves us with 269. There we go. Now we're done. So again, this tells us that negative 7,432 can be written as negative 17 times 453 plus 269. So that's the first example. So our second exercise going to involve a little bit of thinking. Whoops, there we go. Exercise 2. Again, we want to use the division algorithm to prove that every odd integer is either of the form 4k plus 1 or of the form 4k plus 3 for some integer k. Now we might think, well, how do we even start this one? But again, it's telling us that we need to use the division algorithm. So it gives us a good basis there of where we need to start from. So again, let's jump back to the whiteboard here. And let's get us some more space. So exercise 2. So what we're going to do is we're going to let a be an odd integer. Then there exists an integer n such that a can be written as 2n plus 1, because we know all odd integers are of the form 2n plus 1. So this is what we want to be able to do. We want to use the division algorithm to show that when we end up with these two specific cases, it's going to end up with something of the form of this 2n plus 1. We just need to figure out what the n is going to be. So we're going to use the division algorithm, because that's what the question is telling us to do. So use the division algorithm. To divide a by, well, what do we want to divide it by? Well, if I look at the question, going back to my slides here, I have things in the form 4k plus 3 and 4k plus 1. Now we know we can decompose things using the division algorithm as something times something plus a remainder. So the plus 1 and plus 3, those are our remainders. And these 4, those are in common in both. So what I'm going to do is I'm going to divide by 4. I'm going to divide a by 4. So when I do this, I'm going to have something along this 4k plus something by the outcome of the division algorithm. So if I divide by 4, then we know there exists integers, because again, a can be whatever we want it to be. The only condition on b, what we're dividing by, is it has to be greater than 0 or an integer greater than 0. Well, 4 is an integer greater than 0, so this works. So we know there exists a q and r where a can be decomposed as this 4q plus r, where r can be 0, can be 1, could be 2, could be 3. But since we're dividing by 4, the largest it could be is 3, because it has to be strictly less than what we divide by, which in this case is 4. So really, we have 4 possible outcomes. We could have this 4q plus 0, 4q plus 1, 4q plus 2, and 4q plus 3. So we have to try each of these conditions here. So if r is equal to 0, then a is equal to 4q. Now it doesn't matter what q is. 4 is an even number. So if I multiply an even number by an even number, I have an even number. If I multiply an even number by an odd number, I still have an even number. So this tells me that a is going to be even. So if it's odd, it's not going to be of the form where r is equal to 0. Now if r is equal to 1, then a can be written as 4q plus 1. Which I could rewrite this as 2 times 2q plus 1. So now let's let n be 2q, then a is equal to 2, and not 2q anymore, we're going to call this n, plus 1, which is exactly the form we have up here, so a is odd. So this 4q plus 1, I shouldn't be calling this q, I really should be calling these k. I'm using q because of the division algorithm, but it's really supposed to be k in these cases. So just make the switch in your head and keep that in mind. So yeah, the 4q plus 1, that is going to be one of the forms. All right, so if r is equal to 2, same idea, then a is equal to 4q plus 2, which we can rewrite this as, well, I can factor a 2 out of each, so this is 2 times 2q plus 1, well, 2q plus 1, that's going to be some integer. I'm multiplying it by 2, an even number, so same idea as before. Regardless of 2q, whatever 2q plus 1 is, I'm multiplying it by something that's even. This is going to be even. So it can't have the form, if it's supposed to be odd, that r could be 2. So we've showed it can't be 0, it can't be 2, but it can be 1. Now, last but not least, if r is equal to 3, then a is equal to 4q plus 3, which we can rewrite this as 2 times 2q plus 2 plus 1, or I could write this as 2 times 2q plus 1 plus 1. So now we let n to be 2q plus 1, and this gives us that a is equal to 2, not 2q plus 1 anymore, that's n, plus 1, which again has exactly the same form for an odd number. So this tells us if it's odd, it's going to have the form 4q plus 1 or 4k plus 1, or it's going to have the form 4q plus 3 or, again, 4k plus 3. So there we go. That's the end of these two examples.